Balu. So your tutorial has not yet started in chapter 5? Not yet? Got to start today. I think they'll start you off with macroscopic potential energy, kinetic energy. So like I told you last class, I think your mistake's going to be arrows, directions, give and take. So internal energy is like the balance that you have, like your bank balance. Somebody gives you money, your bank balance increases or decreases? Increases. That's like the heat that you receive from outside, from the surroundings. If you spend it, if you do work, the balance goes down or increases? Goes down. So if you do work, balance goes down. It's basically a balance equation, energy balance. So it's conservation of energy. Nothing is getting lost as friction, or we assume that nothing is getting lost as friction. So can you write it down again? If I have heat from the surroundings, my energy goes up. If I do work, my energy goes down. So you sum it up, what do you have? And U does not care what is the path. U is a state function. Path is related to Q and W because they go through an interface. It's a process. You feel Q and W only at a boundary. It's not something that you measure or something that you see. You feel it at the boundary. It's a process. It's a transient process. It's a path function. U is a state function. Yeah, write down, I'm just skipping the macroscopic potential energy and macroscopic kinetic energy for the time being. We already did that last class. Yes? Just make sure you write the whole thing when they ask you a question. Write the entire energy balance equation. You write internal energy, change in internal energy plus change in macroscopic potential energy plus change in macroscopic kinetic energy is equal to the heat that I receive minus the work that I do. Make sure you write the whole thing, don't take a chance. If they say neglect macroscopic terms, then it's only internal energy. Outside terms are not there. Just get comfortable with this, do the problems bravely, ask the tutors questions. If you have any questions, anybody is welcome to come to D220 anytime. If I'm not there, just ask my students where I am. I think they'll tell you where I am. I'll show. So don't make mistakes with the directions. Ask the tutors about directions. Ask them to tell you, or you yourself in the tutorial you should tell the directions. I'm taking heat, so my energy goes up. I'm doing work, my energy goes down. So don't look at the board and try to write the equations. You know, there's a reason I don't like to write too much, because you should learn how to write. No point in me learning how to write. So what is the great thing about this other than conservation of energy? What else does this tell you? What does this equation tell you? Okay, it tells you there's balance. What else? Two things it tells you. two other things. I went to question our attendant. Good. Q&A time. It's energy balance, that's fine. What are the other two things that it tells you? You can stare at it, no worries. Because if you tell me what other two things that it tells you, then you will also tell me what it does not tell you. Yeah, go for it. No worries, say whatever you want. At breakfast, right? Say what, oh no, okay, you can say whatever you feel like and then eat your breakfast. What are the two other things that it tells you? So just like your finance, you have the money, you get some, you give some, you spend some, but you also have different ways of distributing it, different denominations that also you worry about, and where you have distributed and all that you worry about. So I'm giving you a hint. Obviously, D you won't tell about the process, but there is Q and W for you to understand the process.
Regarding the amount that we have retained after gaining and spending.
That is all it will tell. So, very wonderfully put. It gives you only how much. It won't tell you how the dispersion happens of your energy, how it is distributed in your balance. It will just tell you how much balance you have. Very, very good. So it tells you only magnitudes of energy. What's the other thing that it does? So if it tells you only the magnitude of energy, it does not tell you how it's dispersed and how it's distributed. That is your second law. Got it? That is the entropy. So if it disperses a lot, you will say the entropy of your money is high or low? High. So we don't talk about dispersion as of now. We are only talking about magnitude, how much, like he said it. Very good. So it does not tell you dispersion, but it tells you magnitude. What other thing does it tell you? One more. Stare at it a little bit more. One more. One more thing that it tells you. It won't tell you dispersion, it tells you magnitude. Excellent. One more thing. And then you will actually tell me what is first law and what is second law.
It tells us what the things that we can do using that potential.
Yeah, you're referring to the work term. So mainly it brings in work, yes? And it tells you there is always going to be a transfer between surroundings and system. So if there is distribution of your balance inside your system without any external stimulus, does this tell you that? No, it will not tell you that. It will not tell you that. There has to be an exchange between the surroundings and the system. If there is an internal fluctuation inside, like your balance is getting fluctuated inside, this will not tell you that. This will not tell you. This involves exchange between surroundings and systems only. The second law will involve both exchange between system and surroundings as well as the internal fluctuation, both. And this involves work. In that case, when we are talking about dispersion, we do not talk about work. So then what is the difference when we talk about work and when we don't talk about work, and when we talk about only internal fluctuations, when we talk about there has to be an exchange between surroundings and the system? Which one is an unimposed, uninfluenced fluctuation or a phenomena? The one where there is internal fluctuations without any kind of transfer between system and boundaries or surroundings, or vice versa. Which one? Which one is the unimposed, uninfluenced, without any kinetics, without any exchange between surroundings and boundary? The internal fluctuation. That is the pure thermodynamic fluctuation. This one will involve, that day somebody asked me, right, what's the difference between thermodynamic and kinetics? This one will involve kinetics. It will involve kinetics. Work will always involve kinetics, always. So you have to worry about both, because all our processes are not simply left to itself and just do whatever it wants. We always influence our system with external stimulus like temperature, pressure, and we try to make products, and we try to change the state, and we do all kinds of reactions and other things. So there is always an influence of outside, and there is an imposition of some kind. This is an imposition thing. Work is an order. You impose something. If you just leave it to itself, then there will be just internal fluctuation. Doubts? That's the difference. I just went to second law. I just thought when you talk about first law, you should talk about second law. Got it? This one has a clear influence between system and surroundings, and there is the work done. So there is imposition, there is order. You direct something to become something. There is an orientation. So once you do that, there is kinetics involved. Okay, where do we find internal energy? So you know what are the components of internal energy? I think you wrote it last class. Everybody wrote it. It includes both microscopic potential energy and microscopic kinetic energy. So you know the hierarchy. Big material, molecules, atoms, constituent of atoms. If you want to go further down, you can go further down. Electrons, nucleus, and further quantum particles. So where do we have the internal energy values for your numericals now? Today if they do numericals for internal energy, where do you have it? Have you opened the book? I think you have. So you have the steam tables, you have the refrigerants, you have ammonia, you have carbon dioxide. Right next to the volume, specific volume, you have internal energy. The sequence is specific volume, then you have internal energy, then you have enthalpy, then you have entropy. That's it. That's your chapter. That's your syllabus. That's your course. So right now we were just talking about work. So you were worried only with specific volume. Now we are talking about everything, internal energy. So it includes heat as well as work. And where do you have it? In the columns right next to the volume. So do we use the same rule of mixtures? Back again to your phase diagrams. Yeah, you can go from any state to another state and all that thing. Initial state, final state. You can be in a two-phase state. How do you know when you're in a two-phase state? Let's say there is 35% of quality of vapor. How will you calculate U at that point? Where both liquid and vapor are coexisting, and the quality of the vapor is 35% mass fraction. How do you find U? Go to the tables. You have UF You have UFG, you have UG. Put the role of mixtures and find it. Got it? What's the role of mixtures? Write it down one time. I just want to see. Notations, I hope you're all comfortable. S is for saturated liquid. G is for saturated vapor. So everything is there in the table for most of the materials that you will be asked for as questions. Careful, you can either use a temperature table and go to the corresponding saturated pressure and find the U values, or vice versa. You can go to pressures and find the saturated temperatures and find the U value. Same thing, what you did for volumes, continue the same thing. That is why if you get the phase diagram right, these things you cannot make a mistake. If you get volumes correct, you will get U's correct. If you get U's correct, you will get obviously H's correct. If you get H correct, you will get S correct, entropy. So what kinds of problems you might find? A constant pressure, isobaric, or isothermal, or adiabatic. Q is 0. Q is 0, isobaric. What else? Both P changing, V changing. Yes? So why did the term enthalpy come about? I know you guys know a little bit about enthalpy. So you wrote the conservation of energy, you wrote the balance equation, you know all this well, you know that it's a magnitude of energy changes, it involves work, there's an exchange between surroundings and systems. What is the great significance of the enthalpy that showed up? Obviously it comes from this equation only, correct? Yes? Heard of the term enthalpy? Heard of the term enthalpy? Okay. Does it come from this equation? Does it come from this equation? Yes or no? No, the question is, does it come from this equation? From a simple balance, energy balance equation. Yeah, you write it down. Write du, dou Q. What do you want to write for work? Constant pressure, you said. Yeah, put a PdV. Okay. So does enthalpy come from this equation? Or no? Okay, yes. Pardon? Okay, I'll go with you. I'll go with you. What should I do to dq? Dou Q. Why we did this? We could have just left it as internal energy, work done. Why we put up one term, enthalpy? U is also a state function. So, I mean, what did you do? U is also a state function. Oh, you converted path function into state function, no? Is that why you wrote enthalpy? Because dou Q is path function. Huh? That's fine, constant pressure. But you could have just left it like that. Why did you have to very specifically put? I can just leave it like this, right? Nobody will bother if I leave it like that. I can just leave it like that. Why should I term it specifically as enthalpy? U is also a state function. So I'm just trying to see whether in real world in the lab when you're measuring, which one is easy for you to measure? U or H? I should not say absolute values. Change in U or change in H. We cannot measure any absolute values anyway. Which one is more easy to measure? Because you kept on saying constant pressure, constant pressure, constant pressure. So most of our lab experiments are based on constant pressure. It's very difficult to handle pressure changes in many of the experiments, but it is doable. You can do it. But then you also have to imagine if the pressure is changing and the volume is constant, then how difficult it is for you to measure internal energy changes at that point. Yes. So it's better to do constant pressure experiments most of the time. That is one thing. But U does not involve the work term also, correct? Yes? So you have to do two measurements then. You have to use some instrument to measure U, then some other instrument to measure W. And then you have to relate it to how much heat you gave is equal to what you got out of it, correct? Yes? Yes? But instead if you just measured how much heat you gave or how much heat you took, you can include both the changes of internal energy as well as work. Do you want to measure these independently or you just measure this? Which is easier for you? Which one is easier for you? Just do the left hand thing or do independently the right hand thing? Louder? Left hand thing. Obviously measuring heat is the easiest and that is the most practical thing, and doing that at constant pressure is very much doable. It's feasible. Get it? So everything that we measure is mostly in terms of heat transfer. Heat transfer dominates and work is a consequence of heat transfer, not vice versa. Yeah? I hope you understand most of the times we are measuring heat transfer only. And then we worry about how much of it could be work if somebody really asks for it, or how much of it is internal energy change. But as a whole, we always say I supplied this much of heat and then some process happened and that is the end of it. In initial state it was this much enthalpy, final state it reached another enthalpy. So the change in enthalpy is that much and that is equal to this much heat I supplied, and so you give me the money for that much heat. That's it. That's how you bill. Yes? Unless somebody really says, give me how much is the change in U and how much is the change in W, then even there you have a problem. You can actually measure W, but very difficult to measure change in internal energy. So then if somebody really puts you in a corner and asks, no, give me change in energy also, internal energy, then what do? You first measure how much of heat you supplied, then you measure how much of work you did, subtract it, and then you give them the number of what is the change in internal energy. Clear? The most doable thing in the lab is this only. It's very easy. You just have to measure heat. You can use a calorie meter. The name itself, I thought I went through it a little bit in the previous classes. Calorie meter. If you track calories, then you can measure enthalpy changes, and that will involve both internal energy as well as work that is being done. Yes? So you don't, in the treadmill, you don't need an ergometer to tell how much work you did and how much heat you gave out. All you have to do is have some heat transfer mechanism when you are on the treadmill. Measure how much heat you came out of you, and that will be equal to both the work that you did as well as the internal energy change. You don't need separate things. So what processes am I talking about other than running on the treadmill? So this enthalpy changes can be used for what? Your piston problems like expansion, compression, phase change. Phase change, can I use enthalpy will change if I phase change? Graphite to diamond, will the enthalpy change of carbon? Allotropic forms of carbon, will the enthalpy change? Huh? Yes or no? Obviously yes. Water to ice? Water to steam? Okay. Ice to water? What else? If I dissolve sugar in water? Yes or no? Dissolution, enthalpy of dissolution. So can you write down different enthalpies? Enthalpies of phase transition, enthalpies of melting, enthalpy of vaporization, enthalpy of dissolution, enthalpy of mixing. Even if you mix, enthalpy will change. Before unmixed and mixed, your enthalpy will change. It involves both internal energy as well as you put an impeller or a stirrer and you mix, right? There is work also that is being done. Unmixed and mixed, enthalpy of mixing. What else? Enthalpy of chemical reactions. Enthalpy of formation of a compound from its constituents. Nitrogen, oxygen, nitrous oxide. So, enthalpy of formation. Enthalpy of ionization. You can form ions. Enthalpy of hydration. You can have an anhydrous solid and then it will become aqueous. It can bind water. Enthalpy of hydration. Enthalpy of adsorption. Enthalpy of absorption. Enthalpy of combustion. Enthalpy of degradation. Food decaying, food degrading. What else? In your batteries, enthalpy of giving electrons and enthalpy of taking electrons, anode, cathode. Your reduction potentials are nothing but enthalpies, got it? Change in the enthalpy. When zinc gives electrons and copper takes electrons, there is change in enthalpy of zinc before and after it forms an anion. Same thing with the cation. What else is there? Anything else you want to pile on? I think this pretty much includes everything. So it doesn't care about the path. Initial state, final state. Involves both change in internal energy as well as the work that you're doing. So typically if it's constant pressure, I will write PDV like this. Let's say by chance in your numerical pressure is also changing. What will you do? Make sure you remember that it is a path function and do the proper integration. Yeah? For the PDV. Got it? Don't keep on blindly plugging PDV and, you know, make mistakes. What if its volume is not changing? There's just internal energy. There's no enthalpy. This term is gone. So if you have two phase, how do I do enthalpies now? Again, same thing. Right next to the U columns, you have H columns. Do the same thing. Use the rule of mixtures and find enthalpy. So in some numerical problems, you can have cycles going from state 1 to state 2, back from state 2 to state 1. Or you can just have phase change. 2 state to single state to 2 state. I'll do some problems, maybe Saturday. By the time I think you would have done a couple classes, tutorials, then I will do some problems Saturday. I think your syllabus is more or less covered, so let me do some problems Saturday. Don't forget the units. What's the units for enthalpy? So you can have specific enthalpy also. In the questions, careful, if you have specific enthalpy. So internal energy is an intensive property or an extensive property? Excuse me. Okay, rephrase again. Internal energy is intensive or extensive? Huh? It's extensive. It involves both microscopic potential energy and microscopic kinetic energy. H is intensive or extensive? Huh? Extensive. H is extensive. Enthalpy is also extensive. Internal energy is also extensive. These are all dependent on how much material you have. That's why careful in the questions, you might have specific energies. If you have specific energies, you have to ask for mass. How much mass is this? So obviously you cannot measure enthalpies, absolute. You can only measure change in enthalpies. You can measure change in internal energies. You can use a calorimeter and you can measure changes. So for changes, what do you require? You always require a baseline. There must be a baseline. There has to be a baseline. Always it's dH, du. There is no, you cannot measure. There is no, like density, you cannot go and measure H, U. Like thermometer, you cannot measure T. You have to measure only dH. For that, what do you need to do to get dH and du? What is your stimulus? What's your stimulus? Simply H won't change, right? If it does all of these things that you wrote, then the H will change. But let's say it does not do that, and I give you granite right now. I give you granite. I ask you to measure change in enthalpy. What will you do? How will you measure change in enthalpy if I give you a rock right now? You cannot measure enthalpy of rock. There is no gadget, there is no device which you will make contact and say this many joules per gram. No, that won't happen. What will you do? Since you are all quiet, let's increase the prize money. 500,000 points. I give you rock. How will you measure enthalpy? Again, my bad, not enthalpy, change in enthalpy. But how you will set up a reference line? See, I give you a rock right now, you're holding it in your hand. Because what reference line? How do you even know? You don't know anything about the enthalpy of formation. You don't know what temperature to use as a reference line. So I just asked, you give me change in enthalpy at room temperature. That's it. That's all I asked. Yes? If you deform the rock, okay, boom. Possible. And you also did some work. You can't argue with that. Good idea, but very cumbersome. How will you measure change in internal energy? You're still stuck with that though. I agree you hammered and so you know the weight of the hammer and the speed at which it came and the distance that it traveled, so you got your wattage, joules per second. That you got it, but you still cannot measure change in internal energy. Good idea, very good idea, but you're still stuck with one du there. How will you measure change in enthalpy? Rock in your hand. Everybody imagine one rock. Give some energy. Like what? Instead of heat, you just refine it a little bit. Like think like you're in the lab. Instead of when you give heat, what happened? What did you change? The stimulus is change the temperature, and then you will measure change in enthalpy. Got it? You will measure change in enthalpy by using a reference sample. You use a reference which does not respond to temperature change, and then you have rock. To both you change the temperature by the same amount. So if this guy has some phenomena going on, his temperature will either go down or go up. Then you balance the temperature on the reference and you supply that much of heat to keep the temperature same. Then you know you got Q. If you got Q, you got dH. Sorry, wrong again. You got dou Q, change in the heat. And then you got dH. That is very much doable. That is a calorimeter right there. You have to give a stimulus of change in temperature. Your response is change in internal energy or enthalpy. So what is the great coefficient for that phenomena? Stimulus, response. There's a degree of change of stimulus and there's a degree of change of response. Who controls that? The coefficient tells you the magnitude of change of response for a change in stimulus, correct? Just like your Young's modulus. Everybody knows a little bit Young's modulus. If I change, so okay, everybody nodded. Yes, it's very good. So what's the thermal coefficient? Heat capacity. So now can you measure heat capacity? Absolute values? Yes. Can you measure enthalpy absolute values? No. Can you measure change in enthalpy with respect to change in temperature? Yes, that is what heat capacity is. That you can measure. So we actually, when we say temperature of the air is that much, what are we talking about? We are saying the heat capacity of the ambience is that much. That is what controls the temperature, yes? Correct. If the heat capacity is very high, what will happen? Temperature will be high or low? Lower. It will be lower. It's more of a bucket. It can distribute the heat really, really well. If your air cannot distribute the heat really well, who will feel the heat? So it's like a polluted air heat capacity versus clean air heat capacity. Which one feels hotter? So what do you think when somebody, obviously you have all experienced that. So what goes in your mind? What exactly is happening there? So you have carbon particles, you have NOx, SOx, sulfur dioxide, nitrogen dioxide, you have all these pollutants, and then you feel hot. So what is going on in your mind? So the pure air was like, let's say, oxygen, nitrogen, a little bit of hydrogen. So then you have this polluted air. You have solid carbon particles. Then you have SOx, NOx. They can all aggregate, form small, colloids, gaseous colloids they can form. So what, and they make you feel uncomfortable and hot. So what happened there? Their heat capacity is much higher than the pure air or lower? Much lower. Much lower. They are not able to disperse the temperature really well. When they are not able to disperse the temperature will come out as heat and you will feel it. Heat capacity is low. Obviously, if you put more and more solid particles, you will feel hot or you will feel cold. Hot, because the heat capacity goes down. Previously, you had nice, beautiful, light gases, oxygen, nitrogen, hydrogen. They could disperse really well. Their heat capacities were pretty high, yes. And once you got big compounds and this, great carbon solid particles, the heat capacity went down. So then what's the definition of heat capacity? Don't go with your temperature rise, please. 1 degree rise in temperature, don't want. I just gave you a pollutant example now. So what is heat capacity then? Its ability to disperse, that's it. It's wonderful. Its ability to disperse energy. Fantastic. And if it cannot disperse energy, then you will feel the heat yourself. So if it is a pure dispersion, then it is only change in internal energy. If it does work and it disperses, then it's change in enthalpy. Clear? So work, if it does, then you have Cp, constant pressure heat capacity. If it does not involve work done, if it's just internal dispersion of energy, then you have Cv, which is du by dt. dH by dt, du by dt. So your most fundamental property that you can actually measure is heat capacity, and that actually will tell you everything about what's going on. The only con of that is it won't tell you how much carbon was there, what was the mechanism of how carbon formed, how did SOx form, how did NOx form, what is the mechanism of they not being able to disperse the heat. You will not get any of that business. What you will get is a wonderful, huge macroscopic number for the universe, but it will not tell you anything about the mechanisms or the modes and the independent constituents. That it won't tell you. So that is a con. There's a pro and a con. So as a pro, at least you should measure it. Yeah? If you want to understand anything about the universe, you should at least measure heat capacity. So you can compare heat capacity of today to tomorrow, you will get a qualitative information. But it won't tell you about the nuts and bolts. It will tell you, it will give you good evidence something changed. The dispersion has decreased, or dispersion has increased, or dispersion has remained the same. But other than that, you should not get greedy and start telling how it happened and all that kind of thing. There you will land in trouble if you start doing this. Because you don't know, you know the constituents of you. There could be anything that can, you just wrote what all the different H's processes. So there you have to be careful. There you should be very cautious in trying to explain why it changed. It's good, right? At least you can tell that it changed. That's a good start. I think that's a lot of contribution. That's more than enough. So I will come back a little bit next class. Nothing, I have heat capacities. I'm thinking, should I go problems next class or? I'll talk a little bit more about heat capacity and then I think I'll do some problems next class. Catch you guys.